Okay, so my name is Sandro Tacchella, and I'm doing my PhD with Marcella Carola at ETH Zurich. Today I will talk about bulge formation and quenching of redshift 2 galaxies. The main collaborators are Simon, Alvio in Padua, Natasha and Stein from MP, and many other collaborators. So as part of the Synth program, we have combined wide-field camera 3 with Symphony AO data to study the stellar mass growth of redshift 2 galaxies. In particular, we have used 55 orbits of the wide-field camera 3, so using similar data like the people working on the candles field, where we use the J and H band filter. The J and H band filter traces at redshift 2 the rest frame optical light, so we can constrain the rest frame optical continuum morphologies of these galaxies. The J and H band filter also traces the rest frame 4000 angstrom break, so we are able to constrain the stellar masses within these galaxies on scales of 1 to 2 kiloparsecs very accurately. On the other side, we have the 300 hours program of the VLT Symphony AO. Symphony is an integral field spectrograph fed by an adaptive optics model at the VLT. There we use the K-band grating to trace the H-alpha emission line map, which gives you a measure for the instantaneous star formation rate, also resolved on about 1 to 2 kiloparsec scales in the galaxies. In addition, the H-alpha line can be used to study the ionized gas kinematics of these systems. So now, important point is that both instruments have about the same resolving power. This means that we can resolve the stellar mass and star formation rate densities within these galaxies at redshift 2 on about 1 to 2 kiloparsecs. So with this data in hand, I will tackle the following questions in my talk. So how does the stellar mass in bulges and disks build up galaxies with cosmic time? How does the stellar mass surface densities and profiles of redshift 2 galaxies compare to those of the local redshift 0 galaxies? And how does the quenching progress in massive galaxies at early times? So our sample consists of 22 galaxies, and you can see that they cover a wide range in stellar masses and star formation rates at the redshift of 2. So they have star formation rates from about 20 to 400 solar masses per year, and stellar masses from a few times 10 to the 9 to a few times 10 to the 11 solar masses. You see that they form a representative sample of the main sequence at the redshift of 2. So let's go straight to some results. I'll show you here the azimuthally averaged profiles of the stellar mass density obtained from the HSD in red and the star formation rate density obtained from Symphony in blue. The individual lines show you the individual galaxies, while the large dots show you the mean relation. You can see the low mass galaxies here, and there are 3 mass bins going up to the high mass bin. The first thing when you compare the two profiles, so when you compare the stellar mass profiles to the star formation rate profiles, you can see that the stellar mass profiles are centrally more concentrated than the star formation rate profiles. We can quantify this by fitting a simple Sersic law to these profiles, and we find that the Sersic index varies from about 1 to 2.8 for the stellar mass profiles, from lower to higher masses, and we find a Sersic index from 0.8 to 1.2 for the star formation rate density profiles. So you can see indeed that the stellar mass profiles are steeper, and they are especially steeper when you go to the higher mass galaxies. So what does this steep mean, and how does these values of the Sersic index compare to local galaxies? We can compare now to a local sample, to the 10th sample, which was mentioned before by Marcella. And I've split the sample into early type and late type galaxies, also here looking at the stellar mass density distribution. So when we look at this, again, the Sersic index, we find a Sersic index of 1.2 for the late types and of about 3.3 for the early type galaxies. We can now add our galaxies on the top, so our redshift 2 galaxies on the top of these local redshift 0 galaxies, and we find that in the low mass bins, so in the low mass bin and the medium mass bin, that our galaxies follow the ones of the local late type galaxies, so they have similar profile shapes. Looking at the high mass, we can see that the densities match the redshift 0 early types galaxies, not only in the very center, but actually out to quite a large radius, up to a radius of about 2 to 3 kiloparsec. Out in the most outer parts, maybe at 5 kiloparsec and thereafter, there's maybe still some mass missing. So this means that our galaxies have already saturated to local bulge-dominated systems. So now the question is, how does the star formation compare in the whole profile, but also in the very center? So when we focus now on the very center of the galaxies, we can look at the central stellar mass density. So this is the stellar mass density within 1 kiloparsec as a function of the total stellar mass. So all the black and the gray shows you the local redshift 0 galaxies. The colored points, so the large points, show you the redshift 2 galaxies, which I've been discussing before. And the color coding corresponds to the specific star formation rate within 1 kiloparsec. So of course, when you look at the very high mass galaxies, all these galaxies at redshift 0, they are quenched. They have no star formation anymore. However, our galaxies at redshift 2, they have star formation rates of a few times of maybe 100 or 200 solar masses per year. So this means our galaxies are actually very heavily star forming at redshift of 2 because they are on the main sequence. Now, when we look at the specific star formation rate within 1 kiloparsec, we actually find that the specific star formation rate of these galaxies is heavily reduced. So they are not really actively forming stars anymore in their center. So this implies that their star formation is actually mostly in their outskirts. So they are not really forming any more stars in the center. Mostly of the star formation is happening in the outskirts.
Sorry, how do you do the specific star formation rate in the center? Is it just H alpha width essentially? Or?
Well, we have the star. Yeah, we have from the H alpha we go to the star formation. So we know how the star formation is distributed within a galaxy.
Well, you know how H alpha is distributed. How well have you got a handle on dust?
Yeah, that's I can answer this. So the main issue is really that we don't know how the dust is detailed distributed. So what we assume is a uniform dust screen at the moment. But we have played around with additional dust towards the center because there have been studies at low redshift which show that there is maybe a dust variation. But at the moment, we are not able to really constrain how much more dust there is towards the center. And we have actually an upcoming HST program where we get some more UV images of these galaxies, and then we are able to constrain the dust much more accurately. So we have to wait for next year to get some more results on that. So we see that they have reduced specific star formation rate in the center, and therefore they have mostly the star formation happening in the outskirts. Now going to the low mass galaxies, we find that the central stellar mass density at the given mass is actually very comparable to the local redshift 0 galaxies. So this means that a galaxy which is down here can't just arbitrarily move around in this diagram. It has to move from redshift 2 to redshift 0 along this kind of sequence here, which has been mentioned before by Marcella. So this means that when a galaxy increases its stellar mass, it has also to increase its central stellar mass density. So it has to move along this sequence. So now we can go one step further and think of how the quenching has to progress in these galaxies. So I'm looking now specifically only on the very massive galaxies, so galaxies around 10 to the 11 solar masses. So when I look at because I have the information on how the star formation rate here in blue is distributed in a galaxy, and I know also how the stellar mass density is distributed in a galaxy, I can, with a simple model, just add up the stellar mass at the given radius, describing the following law. The main assumption is, of course, that the star formation rate, so the total star formation rate, is following the one of the main sequence. So we are following that this integral of the star formation here is following the one of the main sequence, and then just adding up the stellar mass. The assumption is now that the galaxy is actually growing and growing up to some point where it reaches the profile of the local massive ellipticals. And there it has to stop forming stars because otherwise it would overshoot the stellar mass density at the given radius. So I run this simple model. And you can see it has to stop forming stars first in the center, because otherwise it would overgrow quite quickly the central stellar mass density of the local galaxies. And later on also in the outskirts. So this time scale for quenching implies that in the centers we have much less than a giga-year, maybe of an order of a few 100 million years, and in the outskirts it can go up to a few giga-years. So we see this kind of inside-out quenching, mentioned also before by Marcella. So summing up, the emerging picture is the following. So for the lower mass galaxies, the galaxies below 10 to the 11, they have stellar mass density profiles which look very similar to the late types of the local universe. Since they must stay on this universal sigma m relation, they have to increase their central stellar mass density hand in hand with their total stellar mass. The more massive galaxies, so the galaxies around 10 to the 11, We have stellar mass density profiles which are in the center, but not only there, but actually up to a few kiloparsec, very similar to the bulge-dominated galaxies at redshift 0. So they have already saturated to redshift 0 galaxies. This actually, so when you have to imagine these redshift 2 galaxies have now very high central stellar mass densities, and actually this matches very well the picture which was mentioned yesterday by Adi and Avishai and other people, where you need a lot of gas inflow to build up in the beginning, so before redshift 2 actually, these very high central stellar mass densities. Another point is that the redshift 2 galaxies have already quenched centers, so the specific star formation rate is reduced, and the star formation is happening in the outskirts. And when you do with a simple model calculate how the quenching has to progress, we find that the quenching in the center is much less than a giga-year, and in the outskirts it's several giga-years. So this implies this inside-out quenching. So I'm coming to the end of my talk. Thank you. I'm Swiss.
Comment that relates to this, it would be interesting to think about more quantitatively. You can do the reverse experiment and assume that the central densities in ellipticals will all form in sort of bursts that order this time scale, or order some time scale you estimated from the Schmidt-Koenig calculation, assuming they sort of form continuously, i.e. not in many separate episodes. And if you combine that with the ages of the ellipticals, you can actually reproduce a lot of the sort of high star formation rate and of the IR luminosity functions at high redshifts. So there's clearly a quantitative connection here that would be interesting to explore.
Yeah. Mm-hmm.
All right. Any other questions? Yes.
So I'm a little bit confused. One of the reasons I'm a little bit confused is because I actually don't know how did you use stellar mass maps from like pixel stellar mass maps?
No, so I use two approaches. So one, you can do the stellar mass maps and measure something in the stellar mass map, but they are then not PSF correct. Yeah. And this could be very important. So what we have also done is we have fitted Cersei laws to the chain H band individually, and then we have constrained the color profile, and then going from that to the mass and
But it is kind of surprising because there's been this argument that a given stellar mass that disks evolve in size. I should not say evolve. The disks at redshift 2 are different in size by about a factor of 2 from disks at redshift 0 at a given stellar mass. Yet you don't really see that in your stellar mass profile. So I was a wee bit confused as to how. I mean, it could be that observation is wrong because it didn't do this stellar mass.
Yeah, probably this is measured on the light, and I was just talking about the mass. And it could be that the star formation rate is distributed differently at redshift 2, where you have more star formation in the center, and therefore you have a smaller radius when you will measure it. And later on, you would have a star formation more in the outskirts, in lower redshifts, and therefore you would automatically measure a larger radius. When you look at the stellar mass, it would be the same.
That's actually not what we found when we did color
okay.
in Canvas. So let's talk about that.
Okay, cool, yeah.
Thank you.
It gives you a measure for the instantaneous star formation rate, also resolved on about 1 to 2 kiloparsec scales in the galaxies. In addition, the H-alpha line can be used to study the INS gas kinematics of these systems. So now, important point is that both instruments have about the same resolving power. This means that we can resolve the stellar mass and star formation rate density data like the people working on the candles field, where we use the J and H band filter. The J and H band filter traces at redshift 2 the rest frame optical light, so we can constrain the rest frame optical continuum morphologies of these galaxies. The J and H band filter also traces the rest frame 4000 angstrom break, so we are able to constrain the stellar masses. Okay, so my name is Sandro Tacchella, and I'm doing my PhD with Marcella Carola at ETH Zurich. Today I will talk about bulge formation and quenching of redshift 2 galaxies. The main collaborators are Simon within these galaxies on scales of 1 to 2 kiloparsecs very accurately. On the other side, we have the 300 hours program of the VLT Symphony AO. Symphony is an integral field spectrograph fed by an adaptive optics model at the VLT. There we use the K-band grating to trace the H-alpha emission line map, Alvio in Padua, Natasha and Stein from MP, and many other collaborators. So as part of the Synth program, we have combined Wide-Field Camera 3 with Symphony AO data to study the stellar mass growth of redshift 2 galaxies. In particular, we have used 55 orbits of the Wide-Field Camera 3, so using